Okay, so let's continue with where we left. So in the previous session, we talked about the dominant strategy equilibrium and Nash equilibrium in game theory, and then we started Bayesian Nash equilibrium, but we couldn't finish it. It is a bit long, but we started that. So we said that first we talked about sequential move games, and we said in ordered or sequential move games, the players play the game in order, right? In order. So they don't play the game simultaneously. And the ordered or sequential move game can be represented as an extensive form or a game tree. There was a slight difference between extensive form and game tree, but where in extensive form, at the end nodes we have payoffs, but in game tree at the end nodes we have outcome of the game. We talked about common knowledge, which was an interesting thing. So we said that it means that each player knows the game tree. Each player knows that other players know the game tree. Then each player knows that other players know that. Other players know that, know the game tree, and so on, right? And this goes until forever. And we also mentioned some example and funny example from Friends. By the way, one of the actors of Friends, Matthew, what? The actor of Chandler passed away several days ago. Many people were very sad because they said that Chandler helped them with their sadness and depression, etc., by watching Friends. But now Chandler has gone. Did you know that another interesting thing is that I just read in the internet that while he was playing this funny comedy, he was himself depressed and he was alcoholic, etc. But I'm saying that it's fascinating that he was depressed, but he tried to make others happy. That's interesting. Okay, so we saw some scenes saying that in the episode, the one where everybody finds out, we said that Chandler and Monica are fooling around, and Phoebe, Rachel, and Joey find out that they were having sex, and then Phoebe said, "Let's play again with them. Let's flirt with Chandler and see who wins the game." Kind of a game theory also. And then there was an interesting conversation where Phoebe told Rachel and Joey that they don't know that we know, they know we know. And that was interesting. Okay, that's related to common knowledge as well. So we also talked about, so nature can be one of the players which makes random movements with known probabilities. Yes, it's a non-strategic player, so it doesn't follow any strategy, but its movements are random and also with known probabilities. As a result, when nature is one of the players, the game is random, has randomness. Hence, we can use Bayesian, Bayes rule. And certain game is defined in the literature is that nature does not move after any player, so it starts at the start, but it either does not participate or starts the game. So if it participates in the game, it starts the game. Otherwise, it's not in the game at all. That's called certain game. Symmetric game means that no player has information different from others. And complete game means that nature does not move first, or its initial move is observed by every player, so that all players know what situation the game is in. And we know that when nature makes a move, it determines the situation, right? The situation that the game is played in. I told you some examples. For example, I said, consider Facebook or Meta and Google as maybe duopoly in the market. And the nature decides whether there is a recession or not, right? In the recession, the players will behave differently than in a good economy. So that's one thing, because interest rate is different in recession and in good economy. So yes. Okay, Bayesian Nash equilibrium now. So we said Bayesian Nash equilibrium. It was proposed in 1967, references 1 and 2, and it said that it considers some probabilistic beliefs for every player. And we said we don't panic when you hear belief. Belief in usually means probability. So because you can model your beliefs as probability. And so every player has some probability. Therefore, it is useful if there is some randomness in the game, of course, because we are using Bayes rule, all right? Such as when nature plays a role in the game, right? Moreover, note that Bayesian Nash equilibrium is usually used for ordered or sequential move games. It's because of the next sentence. Each player assumes with some probabilistic beliefs that the other players will have some strategy in playing the game. Then, while the players play the game one by one during the game, the players update their beliefs using Bayes. You see that? Consider, so the players have some beliefs for each other, how they are behaving. And then when someone does something, they will update their belief. I think I wanted to say this example last session. That, let me think, yes. So for example, consider Google and OpenAI, okay? So Google has some beliefs for OpenAI. By the way, you know OpenAI. OpenAI proposed ChatGPT. So Google has some beliefs for how the behavior of OpenAI. OpenAI has some beliefs for Google, right? But at some point, suddenly, maybe, yes, as for example, OpenAI proposes or outputs ChatGPT in the market. And then Google was shocked, right? Google was shocked, and after some months of trial, Google offered BART, I guess. It was initially activated in the US, not in Canada. I don't know why. But yes. So they updated their beliefs and they acted differently because of the act of OpenAI. As you see, it's a sequential game, right? They didn't do it simultaneously. So another way is that consider two companies in the market which are forming a duopoly. Then one of them companies, for example, reduces its prices, right? Assume that the nature also decides whether we'll have a recession or not. And the other company sees the behavior of this first company and updates its beliefs that why did this company do that? So maybe there is a recession, or maybe there is not a recession. So they have beliefs for each other, but when someone does something, they update their beliefs. Okay. By the way, feel free to interrupt me and ask me if you have any question. In the Bayesian Nash equilibrium, we propose an equilibrium and use it to calculate the beliefs. Then we check whether the strategies are the best response for the generated beliefs or not. Okay, so we propose some strategy which usually should make sense. Okay, and we can do that. Usually, the payoffs are in a way that we can propose some strategy which makes sense because these are the real games. Okay, and then we will check. We'll check whether the strategies make sense or not. By Bayes' rule, we see we are probably in which path of the tree. This is how Bayesian Nash equilibrium performs. By the way, so in summary, calculating the Bayesian Nash equilibrium has 3 steps. By the way, let me tell you that this slide deck of Bayesian Nash equilibrium is weird, okay? Even weird for me, okay? So when you study it, don't panic. If you think it's weird, you know that it's weird for Benjamin too, right? So but as it is an important thing in game theory, we have to cover it, and we should know at least what it is doing. So it has 3 steps. First, we propose a strategy profile. Okay, we usually propose strategies which make sense according to the payoffs. We'll see some examples for you to understand what I mean by making sense. Okay, which makes sense according to the payoffs. Note that a rational strategy is usually found as the game is rational game, where some patterns will have some more payoffs. So we usually can find some strategies yielding to a large payoffs, which makes sense because the game is rational game, and the game makes sense itself, right? And we see what beliefs the strategy profile generates when players update their beliefs in response to each other's moves. Okay. And so as the second step, so that was the first step. In the second step, we see what beliefs the strategy profile generates when players update their beliefs in response to each other's moves. But we will see these steps by examples. And then we check whether, given those beliefs together with the strategies of the other players, each player is choosing a best response for itself, right? We should check whether it is choosing a best response for itself or not. So as you see, these 3 steps are exactly summarized in this sentence that I told you. Every player will update its belief based on the other player's movements. So this is the Bayes rule. P, probability of A given B. A and B are random events, okay? Is probability of B given A times probability of A over probability of B. Let's talk about this part a bit in parentheses. This is also good for you to understand Bayes rule in machine learning, etc. So this is called posterior. This is called likelihood. This is called prior of A. This is called prior of B. Okay. So what does posterior? I think for you to understand this, maybe let's give an example. Probability of X given, let me think. Sorry. Yes. Y given X is probability of X given Y. I think I'm right. If I'm wrong, please let me know. Okay. So Y, assuming machine learning, Y is label, X is data. Okay. In machine learning, we usually have data and labels. And if the labels are continuous, they are useful. It's a regression task. And if the labels are discrete and finite, it's a classification task. Okay. So this is, again, as I said, this is called posterior. This is called likelihood. In this case, this is also called, where do I write it? Class conditional. Class, because it's conditions on the class label. This is prior of the class. This is prior of data. Okay. Okay. And for example, have you heard of LDA in machine learning? Linear discriminant analysis. It works with likelihood times prior, which is posterior, right? So LDA works with the numerator of Bayes rule. Here, these two. Or have you heard of logistic regression? So yes, so logistic regression directly works on posterior. This part. Okay. So the probabilistic algorithms in machine learning would work with different parts of Bayes rule, many of them. And why am I saying this? For you to completely understand Bayes' rule. First off, Bayes' rule it seems so obvious. You know the proof? Why? So proof comes from here. Joint probability of A and B, you can write it as probability of A given B times P of B. So it says that what is the probability that B happens? Then given B, what is the probability that A happens? I think it makes sense, right? Right. On the other hand, you can write it probability of B given A times P of A. So probability that A happens times the probability given A happening, the probability that B happens, right? As a result, these two should be equal to each other. When you set these two to equal to each other, you will get the Bayes rule here. Did you get it? Okay. As the proof is so trivial, I have heard that when Bayes, because Bayes rule is named after Bayes, when Bayes found this formula, he put it aside and said it's worthless. it's a trivial equation at the first time. So this is Bayes rule, but let's talk about the parts. Why do we call it posterior? What does posterior mean? First off, posterior is a Latin word. It's in Latin, specifically, it was a posteriori. I don't know what a means in Latin. Apparently, it has some meaning. A space posteriori. Okay, and prior is also a Latin word. In Latin, it is a priori, right? So they have some I at the end. I mean, a posteriori, a priori. Okay, these are two Latin words. Where did they come from? First time, you will be shocked that they didn't come for the first time in mathematics. Yeah, exactly. It came from philosophy. Thank you. So it is about epistemology. I don't know. Have you passed any philosophy course or so? For example, one of the people who has talked about it is Immanuel Kant. Do you know Kant? Also pronounced as Kant, doesn't matter. Kant or Kant. Immanuel Kant is a very famous philosopher, almost revolutionized philosophy, and he was a professor in philosophy. One of his important, so he has three critics. In the first critic, which is critic of critic of pure reasoning, I guess. Yes, the first critic, I think it's 600 or 700 pages. Can you believe it? It's a large book, and it's very complicated. His friend borrowed the book from Kant to read it, and in the middle of it, he returned it back to Kant, said, if I continue reading it, I will get crazy. And Kant has talked about this too. So first, let's see in philosophy, what do they call it a posteriori? So we have propositions. Epistemology talks about whether a proposition is true or wrong. Okay, this is the whole epistemology. Then, an example proposition is what? You tell me. The cell phone is on the table. The propositions might be simple, but are they true or not? Okay, so in epistemology, they talked about these things, that whether some proposition, by the way, proposition is a bit different from sentence. How are you? How are you? It is a sentence, but it's not a proposition. So propositions are either senseful or nonsense. Some of them are nonsense. For example, the ants of my garden are waxing their shoes. Okay, this is a nonsense sentence. Even recently, if you have heard of Wittgenstein, Russell, these people, Wittgenstein has said that even ethical propositions are nonsense. When you say that when you say that, for example, saying the truth is a good thing, this is a nonsense proposition. It is complicated. It's related to the philosophy of language, linguistic philosophy. Anyway, why am I saying this to you? For you to understand Bayes' rule completely. We'll go back to game theory in a few minutes. Posterior comes from a posteriori, if I can pronounce it correctly. It means that, so the propositions are either prior, a posteriori, or a priori. What do I mean by this? A posteriori is understood after experiencing the world. Hence the name posteriori. It's post-experience. Okay? Post-experience. So you experience the world and then you understand it. A priori propositions are understandable before experiencing the world. Hence the name prior. Examples? The phone is on the table. Is it a posteriori or a priori? What? For you to check whether it's true or not, what should you do? You should look at the table, right? So you should experience the world. It's a posteriori sentence, proposition. 2 plus 3 equals 5. Is it a posteriori or a priori? Okay, can you answer me? Priori. Priori. Why? Can you find any 2 in this world? No, we can't. You can find 2 things, 2 tables, 2 persons, 2 blackboards, 2 whatever. You can't find the 2 itself, right? You can't find 3 itself. So these are a priori before even experiencing the world. I think now we understand. By the way, so we have a posteriori, we have a priori, we also have synthetic propositions and analytic propositions. Okay, so synthetic propositions comes from synthesis of 2 things, several things, and analytic propositions, they don't come from synthesis. It's the opposite of synthetic. As a result, how many cases do we have? 2 times 2, 4. So synthetic a priori, synthetic a posteriori, analytic a priori, analytic a posteriori. A good portion of critique of pure reasoning by Kant is talking about these. One of these I think doesn't make sense, although recently in the previous century, Quine is one of the important philosophers of the previous century. I think Quine, it was Quine, I guess, said that the 4th one also makes sense. But one of them was, I think Kant contributed to that. So before Kant, there were only 2 which made sense, but Kant said there is a 3rd one which makes sense, and I think it was, let me think, it was, yes, synthetic a priori. Before Kant, I think, yes, before Kant, people said synthetic a priori propositions don't make sense. Kant said no. An example is 2 plus 3 equals 5. You are synthesizing 2 plus and 3, 2 and 3 to say that it's 5. I think, if I'm not wrong, I have forgotten some details, but I think Kant talked about this. Yes. So anyway, now you understand what a posteriori means, what a priori means. Now let's come to mathematics. Mathematics borrowed these terminologies from philosophy. Why? Can you tell me? Do you know that previously mathematics and philosophy had a strong connection? Have you heard of Descartes? It was before Kant. René Descartes. He talked about duality. So René Descartes was a mathematician / philosopher. When we use Cartesian coordinates, it's proposed by Descartes. When we say a vector, a 2-dimensional vector plus another 2-dimensional vector is the 3rd vector connecting the start of one of them to the end of the other one, right? This is exactly what Descartes talked about it, although he was a philosopher. Kant, did you know that Kant, that is a philosopher, has a paper published about mirrors in physics? So he was a physician too, physicist too. An interesting thing is that Kant was an expert in Newtonian mechanics. He was a philosopher and a professor in philosophy, but he knew Newtonian mechanics completely. He was astonished by that. Okay, anyways, so it came to mathematics, and then in Bayes' rule, they said this can be seen as posterior. Why? Can you tell me? Consider this. Why is it posterior? Yes. Yeah, given x. So it says that given data. So given data. So you experience the data. What is the probability of label, class label? So you experience the data. What about this one? Likelihood. Likelihood is also another name for probability, but they said let's call this likelihood or class conditional, because condition on the class, what is the probability that data happens, right? The priors, I think the names are obvious. The prior of the probability of a class label without even looking at data is prior, right? Without even experiencing the data. Okay, so another thing is that we can marginalize. By the way, in this course, I'm teaching you several techniques, not just game theory and these things. I'm teaching you techniques, yes. It's convention, I can say. It's convention, but usually in machine learning, they say probability of label given data is posterior. Okay, why? Because you experience data to get a label, but probability of data given label is called likelihood. Okay, but when you see it as A and B, then it's convention. Okay, so any other question? No. Now I was talking about this, but I'm teaching you probability as well right now. So this is also called marginalization. We marginalize over A. What do I mean? So probability of B can be written as summation of probability of B given A times P of A, summation over all cases of A. In other words, you can write this part as this too. Probability of joint distribution of B and A, right? Because this is this according to what I just talked here. Yes. So you can say, let's consider the joint probability of B and A, but sum over all cases for A. Then it means that only the probability of B remains, right? So this is Bayes' rule. I think we talked about it a lot. Now let's talk about Bayesian Nash equilibrium, example 1. Consider an example game with the following extensive form, where the nature N, then player P, and then player Q play in order. Okay, so it's a sequential game. The nature starts the game, then the player P, then the player Q. Okay, the game has two players, two strategic players, P and Q. Okay, and a nature which is non-strategic. The actions of player P are P1 and P2, while the actions of player Q and are Q1 and Q2. Okay, so far clear? So I have player P actions P1, P2, player Q actions Q1, Q2. I might have more actions, but for simplicity, currently I assume I have 2 actions per player. Then the actions of nature are also A, B, and C with probabilities 0.7, 0.1, and 0.2 respectively. Do you remember I told you nature, its movements, the probability of its movements are known, is known, right? So the actions are A, B, and C. Consider, for example, A is recession, B is maybe some other thing. So we have several situations, realizations of the game, right? So here is, and at the end, I'm showing the payoffs, right? I'm showing the payoffs. What is the order of payoffs? It's the order of these in the same as the order of appearance in the game tree. So this is the payoff of player P. This is the payoff of player Q. Okay. And now let's see. Step 1. Guys, I need you to focus a bit to what I'm talking, because as I said, it becomes a bit weird. You need to focus. Okay. Step 1, we propose a strategy profile which should make sense. Okay. So the player P observes that the action of nature and then performs in its action. So who can see the action of nature? Player P or Q? Player P performs after nature. Okay, so nature is observable. The action of nature is observable by player P, but when nature plays some action, the player Q still doesn't know what nature has chosen. Player P knows that. Okay, that's one thing. So player P observes the action of nature and then performs its action. But there is a but here. Player Q doesn't know the action of nature, but it can guess. First off, how does it guess? Using two pieces of information. First off, these probabilities of actions of nature are known by all players, including Q. So player Q, even at the start of the game, knows that the probability of action A is higher for nature. That's one thing. Another thing is that then player P plays the game, right? Then the player Q sees which action the player P played. In this case, player Q can guess what nature has chosen. Assume, we will see in the game, by the way, but in linguistic term, assume if you analyze, if nature chooses action A, the player P is better to play P1. Assume, I'm saying that. We will go into the details. But if the nature chooses B and C, it's better for player P to choose P2 according to its payoffs at the end of the tree. Okay. Then you tell me, assume you are player Q. You see that player P played action P1. Can you guess what nature has chosen? Action A, right? Because when I told you the payoffs, for example, of player P are larger for player P if you are in this part of the tree, for example. But now assume player P chooses action P2. Then the player Q will say probably nature has chosen B or C, not A. Because we know that players are rational. Players will not do something which harm themselves, right? That is it. I think now you understand. So we have some probabilities for the actions of the nature, but they get updated by the actions of the previous player, right? For example, player Q knows that A will happen with probability 0.7, but after the action of player P, for example, player P chooses action P2, then this probability 0.7 goes down, right? So it updates its probabilities by Bayes rule. Okay. So that was in explanation in English. Now let's go into math. What happened? Now let's go into math. So the player Q, as I said, does not observe the action of nature, but can guess it according to the action of the rational player P, right? It's important that we know that the players are rational. The prior beliefs of the player Q is that nature moves A, B, or C with probabilities 0.7, 0.1, 0.2 respectively. right? Exactly these probabilities. So far clear? So these are the prior beliefs of player Q. That's why I talked about philosophy. It's prior, right? But after experiencing what player P does, then it updates it by Bayes rule. Okay. The player Q assumes, based on the actions of player P, these things. This assumption makes sense because of the payoffs of the player P at the end nodes of the tree. Let's see. So what are the assumptions? If player P chooses action P1, nature must have chosen A or B probably. Let's see why. So P1, these are P1s, right? Let me clear this part. Okay. So can you tell me, so P1 has these two, P1 has these two, right? P1 has this, agreed? This part of the tree. We want to see which part of the tree we are. Now let's see the payoff of player P in these parts of the tree. So 2, -1, 5, 0, 0, -1. Okay. Sorry, give me a second. Yes. Now see, compare it with the other choices. So these are the other choices, right? Oh no, not compare. I apologize. Give me a second to concentrate. Yes. Compare these three parts. The payoffs of player 1, P. So 2, -1, 5, 0, 0, -1. This is awful. 0, -1 is awful, right? Compared to having 2 here and 5 here, right? So when P1 is done, we assume that probably A or B have happened, not C, right? So probability of P1 given A, as you see, we have conditional probabilities. Or probability of P1 given B is 1. Probability of P1 given C is 0. Doesn't make sense. Because if we are in this part of the tree, if nature has chosen C and the player P chooses action P1, its payoffs will be awful. And we know that player P doesn't want to harm itself, right? Okay. So when action P1 is done, we know that probability of P1 given A and B are 1, but given C is 0. Okay. Now, if the player P chooses action P2, let's see which part of the tree we are. I need to clear this figure a lot. Okay, see. P2. This, and this. So we have these two, these two. So now you see this part. Probably it's the opposite way. Probability of P2 given C. So the probability of P2 given A and P2 given B is 0, but probability of P2 given C is 1. Okay, why? According to the payoffs. Just compare the payoffs. We have 4 here. But here we have 1, -1. We have -1 and 2. But here we have 4. Right? And we know that these two should sum to 1. So I'm saying that you can't say, for example, when it is 1, this must be 0, right? These are the only cases that might happen. So this, okay, and you know that when it is 0, this must be 1. Okay. Now, if player P chooses P1, then player Q chooses action Q1. Let's see why. If player P chooses action P1, we know that we are either in this part of the tree or this part of the tree, right? A or B. Then if that's the case, let's see. Where were we? As I said, it needs concentration. Otherwise, you will not understand what I'm saying. We'll be here, right? When a player P plays P1, we know that we are in the part of either A or B. So these are the payoffs. Now let's see. If the player P chooses P1, then the player Q chooses Q1. Why? Let's see. Because Q in this part of the tree, these are better than these for payoff of Q. Do you see what I'm saying? Do you see or no? Compare this. 2 minus 1. 2 is better. Minus 1, 1. Overall, I'm saying that. In more cases, in most of the cases. 1. 1, 2. Give me a second. I got confused a bit. Q. Player P chooses. Player Q chooses action. Yes. So if player P chooses action P1, then player Q chooses action Q1. Yes, according to the payoffs. But if player P chooses P2, then player Q chooses action Q2. This strategy makes sense because of the payoffs of the player Q at the end nodes of the tree. Again, let's see P1. So let me explain it again. So when player P plays the action P1, we know that we are in the path A or B. In this case, compare these, and you will see that for Q, it's better to do Q1, according to the payoffs. But when the player P plays the action P2, we must be probably in the path C. So we are here. Comparing these, we'll see that because of these 4 here, it's better for Q to choose Q2. Okay. By the way, don't panic. I will not bring any question from this Bayesian Nash equilibrium in the exam. Okay. I just want you to understand. So try to listen without stress. Okay. Try to understand what Bayes is doing. Yes.
What P makes a decision based on what Q would do?
No. P doesn't make decision based on what Q do. It's the other way around. Q performs the action based on what P does. No, they all know about the payoff. So the tree is known by both P and Q according to the common knowledge. Do you remember? According to this, all players know what the game tree looks like, and including the payoffs.
Yeah, but then P would anticipate what Q would do and would make different decisions then.
No. When P does the action, it's over. It cannot change its decision.
Well, but since P knows the payoff of Q, then he would anticipate what would maximize his payoff based on what Q would do.
That's exactly what I'm saying, that this is an ordered game. When the player P does its game, it's done. It cannot redo its action. Then player Q enters.
Well, let's say
okay.
Assume that if P1, P to P1,
okay,
it would increase the probability of D. But the fact is, if P was smart, it would choose P2 because Q would choose.
So, sorry, which part of the tree are you talking about? The middle, okay? Here. Okay.
Q will choose Q2.
P2, Q2.
So what the expected value of P, the highest one is to do P1.
That's exactly what I'm saying. Why are you saying that we are in P2? We are not in P2 here. Because we know that here it is in path B and it must be P1. I think you forgot it. Here we just analyzed it. If P1 is done, we are in path A or B. If P2 is done, we are most probably in path C. So it's not possible that we are in path B and P2 has been done. According to the beliefs of Q, I mean.
Well, why? if they are in path P, P should do P2.
No, I disagree. Why? Because of this 5 here. This
Is expected. It does, but it knows that Q would always choose Q2.
who says that the expected value is greater? 5, 0 is better than -1, 2.
P does P2. The reward of Q, if P does P2 is 3 versus -1. So it knows Q will choose the third. Which means that by choosing P2,
Yes, but
yeah,
so I'm saying that here, I'm saying that rational P will not choose P2.
but it didn't know. The tree.
Okay? You say that this is better than this bar? Do you say that?
Yeah, because if P does P1,
Okay.
Q will do Q2. If P does P2, Q will do Q2 as well. So which Q2 is best? The one from P2.
I disagree with your sentence. If P plays P1, Q will choose Q1.
Well, if P does P1, Q has a choice between 1 or 2. He would rather choose 2.
No. See the whole this part. Because Q, so the question is, if we are here, player Q will choose Q2.
Yeah.
If P chooses P1. But how does player Q make sure that we are in path B? Maybe we are in path A as well. That's why I'm saying that. As player Q has doubt whether we are in path A or path B, it should consider all of the sub trees in these two paths. It's an aggregated decision. It should, the player Q and player P in Q, they should see the payoffs at all of the children of those paths. How does so you're saying that we are here, but I'm saying that player Q never gets confident that we are here. Maybe we are here. Because both of these subtrees make sense for player P.
So P1 doesn't know where it is.
What? P1 assume
P assumes that Q doesn't know where it is, which is why this works.
it's the whole thing is probabilistic, yes. But player P knows that player Q can guess according to its action. That's exactly the common knowledge that I talked about. So player P is completely aware that player Q cannot make sure whether they are in path A or B, but player P still knows that player Q can guess that they are in path A or B. And it knows that probably we are not in path C because I chose path P1. Yes.
Both players would submit their guess at the very beginning. They can't change their.
No, it's sequential. So player P chooses the action and then not changes. And then player Q enters.
The current state.
Current state of what?
The tree.
No. So whatever level of the tree we are, we only know the previous part. So for example, P knows what nature did. Q knows what P did, but doesn't know what nature did. Can guess what nature did. Did you get it? Okay, that's interesting, right? So the analysis is interesting. The guessing part is interesting. Okay, so let's continue. Then step 2. Now let's do the math. So step 2, we see what beliefs the strategy profile generates when players update their beliefs in response to each other's moves. So updating the beliefs of player Q, do you remember player Q had some beliefs? Now it's time to update because of the action of player P, right? So about the nature, if the player P chooses action P1, so now consider both cases. If the player P chooses action P1 or if player P chooses action P2. First, P1. Then we know that we have 3 states of the nature. A, B, C. So probability of A given P1, B given P1, C given P1. Yes. No. So player Q knows what P did. As I said in the tree, whatever level we are, we know the previous what previous layer did. Okay, for example, when it's time for Q to decide, it knows what P played, but it doesn't know what nature chose. It can guess according to rationality of P. Okay. And here is the common knowledge that I'm saying, that player P also knows that player Q can guess by its action. So player P is about cautious. Should I do something that player Q gets confident that we are in this path? Right? Okay. So that's exactly that episode of Friends, right? So probability of A given P1, again, Bayes rule. Probability of P1 given A times P of A over, do you remember the marginalization that we had? It's probability of P1 given A times A, P of A, plus probability of P1 given B times B, P of B, plus probability of P1 given C times P of C. Now let's put the numbers. What was P A priors of A, B, and C? We had them 0.7, 0.1, 0.2. You remember in the tree? We had them here. We had them, right? These were the priors. What about these? We just analyzed them. The probability of P1 given A, B, and C. We analyzed them here according to the payoffs in the tree, right? We analyzed them. So we put 1 or 0 for them, right? By the way, you might be wondering, why did I put 1 or 0? You'd never asked me this question. I said, if player P does P1, it's better for player P to be in path A or B. And I set their probabilities both to 1. But maybe path A is better than path B for player P. So they might not have equal probability, right? I will relax it later at the end of the slide deck, okay? But for now, for simplicity, I assume 0 or 1, binary case, which path we are or not, probably, okay? So here we put 1s and 0s, and we calculate these. What are these? What are these three? What is this 0.875? That was the 0.7 of P of A that got updated. So what do I mean? Player P plays action P1. Before that, before even the start of the game, player Q assumed that nature will probably go choose action A with probability 0.7. Suddenly, player P enters the game, does P1 action, and now player Q says, oh, probably we are in state A of nature with probability 0.875, not 0.7. It got updated. It updated its belief. Okay? Updated its belief. And we also, 0.1 got updated to 0.125, and 0.2 got updated to 0. For this case, by the way, for the case when action P1 was chosen. Now, the other case. The player P chooses action P2. Okay. Then what happened? Probability of, so let's see. So again, according to the Bayes rule, so I have these conditional probabilities. And here now I have P2, 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 as you see. Again, we calculated these probability of P2 given A, B, and C here. We analyzed them according to the payoffs. Then we put them in these equations. So if P2 is done, 0.7 gets updated to 0. And it makes sense, because if you are in path A, player P shouldn't choose P2. It's bad for it. And we know that player P is rational, right? So 0.7 suddenly becomes 0. 0.1 gets updated to 0. 0.2 gets updated to 1. Player Q says probably we are in path C, right? Step 3, we check whether given those beliefs together with the strategies of the other players, each player is choosing a best response for itself. Let's see. The above calculations show that if player P chooses action P1, the player Q believes that the nature has chosen A or B with probabilities 0.875 and 0.125 respectively. We just calculated that in the previous slide. If player P chooses action P2, again, we calculated by Bayes' rule that player Q believes that the nature has definitely chosen C with probability 1. We calculated it here, right, in this slide. Now, as a result, according to the above analysis and payoffs in the tree, by the way, these probabilities were chosen according to the payoffs by the analysis of the payoffs in the tree. Remember that. And that's why I said we usually choose the strategy which makes sense by this analysis. As a result, according to the above analysis and the payoffs in the tree, player Q chooses action Q1 if player P chooses action P1. Okay? That analysis that we have. Also, moreover, player Q chooses action Q2 if player P chooses action P2. So now we found a strategy of how they should play the game. Okay? Note that if nature has chosen B and player P has actually chosen action P1, it would have more payoff for player Q to choose action Q2. However, as it is more probable that nature must have chosen A, given the action P1 of the player P, it makes sense for the player Q to choose action Q1 after the action P1 of the player P. I will let you know what it means. I think you got confused. See, let's go back to the tree. Okay. Yes, yes. Let me clean this part. Okay, so assume player P chose action P1. And we know that we are probably in path A or B, right? But let's see, we saw that, now let's see Q, we said that when it makes sense for Q also to choose Q1. Let's see. Here we have 2, here we have -1. Of course, Q1 is better. What about here? So here, we have 1, we have 2. Q2 is better. But why did I choose Q1? So first off, if both of these would consensus, we would do that. Assume in this case also this was 3, this was 2. Then I would say Q1 is better after P1, right? Agree? But now I can't consensus because player Q should either choose Q1 or Q2. One of them. Which one? This is the question. I know that I'm in path A or B, and in one of the paths, Q1 is better than P1. In the other path, Q2 is better after P1. Which one is better to do? Now let's see probability. What is more probable? Path A or B? A. So as a result, Q1 is better to do than after P1. Agreed? Okay. So as you see, it needs a lot of analysis. In summary, the strategy of players in the Bayesian Nash equilibrium is as follows. If player P chooses action P1, so the nature must have chosen A with higher probability or B with lower probability, in summary, right? So when the player P chooses action P1, we are in A or B, but A more probable, right? Then player Q chooses action Q1. We just analyzed that in the tree. If player P chooses action P2, so the nature must have chosen C with probability 1, according to the Bayes analysis that we had. Then the player Q chooses action Q2, according to the payoffs in the tree, right? So this was in summary. Note that here, now I'm relaxing that part that I told you. Note that here the proposed strategy was deterministic. The game tree was random, was stochastic, but the strategy was deterministic. We can make the strategy also probabilistic. That's called mixed strategy. We'll see it in this lecture, in the next slide deck, okay? So that's called mixed strategy or stochastic strategy, whatever we call it. For example, we could have proposed the following strategy. The player P chooses action P1 with probability 0.5 in a state A of nature, with probability 0.4 in a state A of nature, and probability 0.1 in a state C of nature. You see? Do you remember? So, by the way, player Q is saying that. This is player Q's belief. Okay? Yes. What? Oh, sorry. Yeah, sorry. It's a typo. Thank you. So, do you remember in the previous slides, we said, is it according to the belief of player Q, if we are in path A, it would definitely choose P1. Here we say no, not definitely, with some probability 0.5. If we are in path B, previously we said it must have definitely chosen P1. Say no, with probability 0.4. If we are in path C, previously we said definitely not P1. So the probability of P1 was 0. We said no, not 0 this time, 0.1. It's a small probability, but not 0. Right? And of course, these probabilities should sum to 1, because P1 either in path A or B or C. Right? So in this case, the conditional probabilities would become this. So previously these were zeros and ones, these conditional probabilities, but now they became probabilistic. Right? And as you see, the result of the update of the Bayes rule is a bit different from what we had in the previous slides. Agree? Likewise, it is possible to have mixed strategies for action P2. I haven't written it, but this was for P1. We can have the same analysis for P2. Okay. So example 1 is over. But I thought that maybe example 2 also helps understand. It took me a lot of time to design, especially example 2. Okay. So consider this tree. Okay. So here we have 3 players now. Consider an example game with the following extensive form where the nature N comes, then player P, then player Q, then player R, play in order. Okay. The game has 3 players, P, Q, and R, and the nature, of course. The actions of player P are P1 and P2. Actions of player Q are Q1 and Q2. Actions of player R are R1 and R2. Okay. The actions of nature are A and B with probabilities 0.5 and 0.5 respectively. So sorry, I need to change this. I had changed the tree, but I didn't change this sentence. So are A, B, and C with probability 0.3 each. So in this case, player Q and R are completely vague. It's ambiguous to them which state we are. With equal probabilities, we are either in path A or B or C. Okay? And these are the payoffs. So let's see. Step 1, we propose a strategy profile. The player P, first off, nature does it, yes. Which one? Which part? These three, I mean 0.3333. Okay, I mean that. They must sum to 1, yes. Okay, thank you. So the player P observes the action of nature. Of course, nature does its action. Player P observes that. Player P plays it, some action. Now we say that player P observes the action of nature and then performs its action. The player Q does not observe the action of nature, but can guess it according to the action of rational player P. Then the player R does not observe the action of nature, but can guess it according to the action of rational players P and Q. Okay. So the prior beliefs of the player Q is that nature moves A, B, or C with probabilities 0.3, 0.3, 0.3 respectively, right? Then the player Q assumes based on the actions of player P, and this assumption makes sense according to the payoffs in the tree, we'll see them. So if the player P, by the way, I chose these payoffs in a way that this analysis makes sense, right? Because it must be a rational game. So I'm saying that these payoffs are not random. That's what I mean. When someone designs this game, the payoffs should make sense, right? These are not random payoffs. So if the player P chooses action P1, nature must have chosen B or C probably. Let's see. So P1 must be probably B and C. Let's see. So P1 is this, and this, right? Let's see what parts it falls. So what subtrees? These are for P1 of path A. These are for P1 of path B. These are for P1 of path C. Agreed? Let's see what's going on here. So now let's see which is better for the payoff of player P. So -1, 2, -2, -1, 3, 5, 2, 1. Good. No, we are not here. Sorry, we are not here. I'm a bit tired. So we are not here. We should compare these. So this is not that much good. This 3 -1, 2 -1, -3. No, 3 -1, 2 -1, 3, 2, maybe, yes. -1, 3, -1, 5. Good. This is not much good. Right? According to this analysis. And now, as a result, probability of P1 given A is 0 because it was not good. What probability of P1 given B and C is 1. Agreed? Now, so the other way around is for the other one. The player P chooses action P2. If probability of P2 given A is 1, then the other paths is 0. We can also analyze that. Let's go back to the tree P2. Let's do the same analysis for P2. For P2. Which subtrees are we in? Here, here, here. Okay, so 3, 5, 2, 1. Good. -3, -2, -2, -5. Awful. -3, -1, -1, -2. Awful. Right? And we just analyze. Now by the way, it continues. Now player R. Player R assumes based on the action of player Q after the action of player P. Okay? So, by the way, Do you remember I told you in the game tree, everyone knows only the previous layer? Let me correct myself. Everyone knows everything before that except the nature. Okay, so player R knows the actions of player P and Q. Let me complete my sentence. So only player P knows the action of nature. Player Q only knows the action of P, but not nature. Player R knows the action of player P and player Q, but not nature. So only the first player knows that action of nature. Okay, yes. Wait, which one? Which question? These P1 given A, P1 given B, P1 given C, P2 given A. No. So whatever comes after this is given. Okay. So now player R knows what player P and Q did, but not nature, right? So if players P and Q do actions P1 and Q1 respectively, then nature must have chosen B probably. How does it know? It simply sees the payoffs. Let me clear this part. What case was it? P1 and Q1? I forgot. So P1 and Q1. P1 and Q1. So when P1 and Q1 is done, let's see which subtrees we are. So as you see my technique here, right? I'm singling out the subtrees, which subtrees we are in. So P1, Q1, P1, Q1, P1, Q1. Where were we? We are here, or here, or here. Agreed? These three subtrees. Now, player R checks the payoffs of player P and Q in these subtrees. So -1, awful. 2, 3, maybe. Good. 3, 5, good. -1, not that, a little bad. -1, bad. 3, -2, bad for Q. So probably we are not here. What was the analysis? So as you see, we are probably in path B, but not A and B, A and C. Let's see. Because of this. So it's not good for player Q. So I eliminate that because we know that player Q is not crazy, right? When I say rational, it means that it's not crazy. This one, also this one, why did I say 0 for that? I don't remember. This was my analysis, by the way. I didn't look it up anyway, but I said it's 0. Anyways, this is my analysis. But if players P and Q do, P1 and Q do, let's go to the tree. Let's go to the tree. So my analysis is that we are in path C, P1 and Q2, P1 and Q2. P1 and Q2, P1, Q2, P1, Q2, P1, Q2, which we are here, we are here, we are here. I can never memorize my sentences. So we are probably in path C, not A and B. In path C. Yes, because of 5 and 2 are very good, but -1 and 1, not that much better. Just give me a second. It's good. This is awful for player Q. -5, -2, awful. Player Q is not crazy. What about this one? It's awful for both P and Q. As a result, we are this probability is 1. We are in path C, but not in A and B. Yes, your question. So every player says that given the actions of previous players, which part of the tree we are probably. So that's the next step. So first we find out which makes sense, which part of the tree it makes sense to be in, and then we use that in the Bayes rule to update the probability of being in that path. Don't you remember what we did in the previous example? So for example, these conditional probabilities were analyzed according to the payoffs, but these priors got updated. This probability of A got updated to probability of A given P1. You see that? Now Bayes rule becomes, in example 2, becomes a bit more complicated because we have 3 players. Okay. Now you can imagine what happens for 4 players. So then it needs computer programming, I believe. So you understood what I did, right? And for the other cases, you go and check at home which subtrees there are, and you will completely find out that these make sense. Okay. So let me say in summary, P1, Q1, probably we are in path B. P1, Q2, we are in path C. P2, Q1, we are in path A. P2, Q2, we are in path A. Right? Okay. Now, if player P chooses P1, then player Q chooses action Q1, then player R chooses action R1. Let's see why. So when it is P1, let me tell you one analysis, and then I say that you do the other analysis yourself. So when we are in P1, we already, I think, said it. We already said it here. Where we are in P1, we are probably in B and C. Do you remember? We said this is P1. We singled out the subtrees and said we analyzed it, and we said that we are probably in B and C, right? Then we also said now again Q1 and Q2. We singled them out the subtrees and we analyzed where we are probably according to the payoffs. And at the end, now you know which subtree you are, which path you are. Then also see the payoffs of player R, the last payoff, to see what the player R will choose, right? Then you can find out the strategy, which makes sense, right? And this is a strategy: P1, Q1, R1. If it is P2, it makes sense for Q to be Q1, then R chooses R2 according to the payoffs in the subtrees. Okay, this strategy makes sense, as I said. Now step 2. Let's go to the Bayes rule to do what you said. Okay, so probability of A given P1. So updating the beliefs of player Q first, and then we update the beliefs of the player R, right? So player Q, probability of A given P1 is as before, we had it. So this is 0.3, 0.3, 0.3, 0.3, and this is 0. This is 1, 0, 0, 1, 0, according to our analysis in the previous slide. We put them and we update them. We do the same for this. Okay, so when, for example, probability of A was 0.3, it got updated to 0, right? Probability of B, path B was 0.3, it got updated to 0.5. Okay, by the way, probability of C also is the same. Was 0.3, it got updated to 0.5. As you see, they should sum to 1. So previously it was 0.3, 0.3, 0.3. Now it became 0, half, half. Okay. Now updating the beliefs of Q if action P2 is done. That was for action P1. Likewise, we calculate for path A, it becomes 1. For path B and C, it becomes 0. So it was previously 0.3, 0.3, 0.3. Now it becomes 1, 0, 0. Okay. Now, for player R, How do we update its beliefs? I think you can guess. We need chain rule in probability. Okay. So according to the chain rule in probability, we have this. Probability of A, P1 and Q1 is probability of Q1 given A and P1 times probability of A and P1. So this is prior is here, right? Likewise, we can write it as, we can further simple this second part to these two, decompose it into these two. So in general, it becomes probability of Q1 given A and P1 times probability of P1 given A times probability of A. This is chain rule in probability. Okay. Updating the beliefs then become for player R. So what do? We say that given that player Q chose action Q1, what is the probability of A and P1? It's this. The formula was too large that I couldn't write it in one line. So I broke it down into, this is a fraction of the base rule. Okay. And as you see, this is the denominator. Okay. So now you put stuff in it according to the analysis that we had. 0, 0, 0, sometimes 1, 1, 0, 1. And these are the priors that we had. 0.3, 0.3, 0.3, 0.3. So you put it, you calculate it for all of these three. Probability of A and P1 given Q1, B and P1 given Q1, C and P1 given Q1, right? And you calculate them. So it became 0, 1, 0. In other words, it was 0.3, 0.3, 0.3 in the belief of player R. Now it became 0, 1, 0 in the belief of player R if Q chose action Q1. Okay. Now, what is this? So again, Q has chosen action Q1, but the probability that we are in path A, but P chose P2. The previous one was P choosing P1, but this now is P choosing P2. As I said, this is a bit complicated, but we need to focus. So when you put the numbers in it, it becomes 1, 0, 0. So 0.3, 0.3, 0.3 in the belief of player R becomes 1, 0, 0. After playing action Q1, this probability gets 1, and the other ones become 0. Now, as you can guess, we have 4 cases, right? P1, Q1, P1, Q2, P2, Q1, P2, Q2. So I'm calculating all of those cases. Probability of A and P1 given Q2. Okay. So you put the stuff, it becomes 0, 0, 1. So 0.3, 0.3, 0.3 became 0, 0, 1. The fourth case, A and P2 given Q2. So you all and B and C. So you calculate, it becomes 1, 0, 0. So 0.3, 0.3, 0.3 became 1, 0, 0. Right? Now, step 3. We check whether this makes sense or not. The above calculations show that if player P chooses action P1, the player Q believes that the nature has chosen B or C with probabilities half and half. We just calculated the Bayes rules. It gave us these numbers. So if P1 is played by player P, Q updates its beliefs from 0.3, 0.3, 0.3 to 0, half, half, right? If player P chooses action P2, player Q believes the nature has definitely chosen A with probability A, right? Okay, probability 1. If player Q chooses action Q1, player R believes that nature has chosen B, and player P has chosen P1 definitely with probability 1, according to the Bayes rule that we had. So for these was after the action of player P. These for after the action of player Q, right? If player Q chooses action Q1, the player R believes that the nature has chosen A, player P has chosen P1. And if the nature has chosen B, player P has chosen action P2. So basically, these two lines are after action of player P and the update of belief of player Q. This one, however, is after action of player Q and the update of belief of player R. Okay? Yes.
There are 3 points where player Q chooses something. Or okay, player Q chooses action Q1. Player R believes that nature has chosen B. That's fine. But player Q chooses action Q1. Player R believes that
Which
nature chooses A.
so which line are you talking? These line? Okay. If player Q chooses action Q1, the player R believes that the nature has chosen B and player P has chosen P1. Definitely. Okay. So every player sees the action of its previous player and can guess what other previous ones did. This is exactly what we are saying, right? So basically, let me tell you the story again. In two first bullet points, player P does something, player Q guesses the action of nature by the action of player P. In bullet points 3 and 4, player Q does something, player R doesn't know what nature and P did, but can guess what nature did, what player P did, according to the action of player Q. Okay? And in this case, they are restricting the subtrees to see which subtree we are, which path of the tree we are in. If player Q chooses action Q2, the player R believes that if nature has chosen A, player P has chosen P2, and if nature has chosen C, player P has chosen P1. You might find this confusing, but now you can understand how hard it was for me to design this exam, right? Designing this was also misery. As a result, according to the above analysis and the payoffs in the tree, this is the strategy. If player P chooses action P1, so the nature must have chosen B or C with equal probability, half and half. Then player Q chooses either action Q1 or action Q2. Subcase 1, if player Q chooses action Q1, player R chooses action R1. Subcase 2, if player Q chooses action Q2, player R chooses either R1 or R2. These are according to the payoffs at the end of the tree. Why am I having subcase? So because player P chose P1, player Q can either choose Q1 or Q2, is kind of indifferent according to the payoffs because of the probability in the Bayes rule, half, right? Player Q chooses either Q1 or Q2 according to the probability and the payoffs at the end of the tree. Then two subcases happen. If Q chooses Q1, R chooses R1. If Q chooses Q2, R chooses R2. Okay. If player P chooses action P2, so the nature must have chosen A with probability 1, then player Q chooses action Q1. Then player R chooses action R2. In this case, we don't have subcases because player Q knows what to do. Right? Is not indifferent. Any question? Yes. This is the assumption. So the question is, why are we making the assumption that only the first player knows the action of nature? Let me generalize your question. Why are we assuming that every player only knows the action of the previous player? This is the so this is the assumption that they make in the ordered games, I believe. Why do they do that? I can answer you in this case, in this way. So here we assumed that every player only sees the action of its previous player. And as a result, only the first player sees the action of nature. right? And we calculate it based on this assumption. If you say this assumption is wrong and everyone can see everything before, including the nature, everything, the calculations will be different. You have made another assumption, your base rule calculations, as everything gets different, right? And also, I think, answering your question in another way, if players know what nature did, this becomes a deterministic game. It will not be a stochastic game. I believe. Let me think. At least it doesn't become completely deterministic. At least the level of randomness becomes lower, much lower. Because if everyone knows that we are in this path of the tree, then what's the randomness in this game? That's the reason that we want to have some randomness in this game. And in real world examples, we might have these scenarios. For example, I don't know what example I can make. Consider some case in the market, although it's not that much realistic, but you can find other examples too. Assume that one of the companies finds out whether there is a recession or not. The other one doesn't know yet. The other one can guess whether there is a recession or a recession is coming based on the action of the previous player. I think it becomes realistic when some of the companies have some people in the stock market, right? For example, maybe a billionaire has some investment in some stock, and the billionaire is a friend of the CEO of one of the big companies. That the billionaire will say, tomorrow, I want to get all of my money out of the stock. You do something. The third company or second company, they don't know this because they are not friends with the billionaire. But suddenly they see that the first company did something weird. They can guess probably tomorrow something happens in the stock market. Right? So we see that a lot in economy. I think Trump did it once. Trump did it, or Elon Musk did it. Elon Musk did it, right? In Bitcoin, I remember. Elon Musk suddenly dropped the price of Bitcoin. This is exactly what happened. Yes.
Does P1 know all of the payouts for each branch for Q and R as well?
Everyone knows the tree. The payoffs at the end of the tree.
So is it or so the player P, when it's looking at whether to do P1 or P2, to essentially look at Q and R's payouts and say, okay, this branch has payouts for Q and R. Even though it had better payouts for me, Q and R would never pick certain values, and so I should go pick another branch.
Okay, so that got complicated. So you're saying that player P, which starts the game after the nature, does some kind of reverse engineering, saying that let me do something weird that I harm the other ones, something like that.
For each individual outcome in the branch,
Yes.
see that one of the payouts, even though it's the best payout there, the Q and R payouts are going to be worse, and so they wouldn't pick that one single branch. And maybe in a different branch there are better payouts for it. That's not necessarily the highest, but it's more like it's basically Q and R would pick those.
Yes. Yeah, I understand. I think
so that's still a rational decision, right?
Yes.
The max payout, and so you like how you determine that for sure. Like this is the way that P is thinking when you're in Q or R.
Yes, so it's a very good question, saying that okay, player P assumes that once after the nature does something to maximize its payoff, but it also at the same time looks at the payoffs of the player Q and R and see if I do that, although it's good for me, but probably players Q and R will do something which will not be good for me in this path. This is exactly the update that I told you. Let's update the beliefs and check whether it makes sense. If not, then you need to do the step 1 and 2 and 3 again. That's one thing. First of, but here, at least in my calculations, I assume that player P, as it does the first move has more power to choose what it wants to do, and then player Q and R update their beliefs. But you can go back and forth between them. I agree that you can go back and forth between. So here, for example, we said probability of A given this probability of P1 A given P1. Let me think. Okay, we said probability of A given P1, and also we said probability of A and P2 given Q2, right? So for example, we said P2 given Q2, you are saying that let's say also Q2 given P2, something like that. So the other way around. I think we can do that. We can do that, but it becomes very complicated. One thing. Another thing is that we should note that first player knows about the action of the nature. So at least the state of the environment, which is path we are A, B, or C, this is not a random variable for player Q, for first player. But I agree, eliminating that random variable of A, for example, rather than P2, probability of P2 given Q2, you can also calculate probability of Q2 given P2, the other way around.
Were you having Q2 look at what P1 did? Because when we were looking at what P1 should do, we only looked at its payouts, it only like which one's the best, essentially, which branch looks like the best once nature happened.
Yeah.
Right? But
Yeah.
then we didn't look at the other payouts. So is that what Q is all assuming? Okay, it's only looking for its own best payouts and never what I'm
at least when Q was guessing, updating its guess, it was saying that player P was rational and what path it chose for it to be better. But I think in our analysis, let me tell you in this way. Do you remember I went back to the tree a lot and checked these payoffs in the subtrees, assume these subtrees, I checked these payoffs. I think you can at the same time check all of the payoffs for player P. Of course, for example, we are considering player P1, you want to update the beliefs of player Q. Of course, you need to look at these, but at the same time, player Q can probably look at the payoffs of Q and R and decide which to do. It's a back and forth thing. Again, it goes back to the common knowledge. What you are saying is exactly rooting in the common knowledge. So player P says that player Q and R know that I do something which is good for me but bad for them. But I also know that if I choose this path which is good for me, probably they will, as they are enemies of me, they will do something to reduce my payout. So it's a back and forth thing. And this is step 3. Checking is for exactly this. So if you in the step 3 you go and check, see the payoffs and see that it doesn't make sense, you need to go back and redo your analysis in step 1. Do you remember in step 1 was analysis, step 2 was the Bayes rule, step 3 was checking. That's the checking. You have a question? No? Okay. I agree this is weird. But I think at least in this slide deck you understood Bayes' rule very well. Yes. What is the motivation of game theory? I think game theory is important for several reasons. First off, life is game theory. And in academia, we shouldn't only learn engineering, we should learn life as well. That's one thing. I myself learned a lot of things about life in academia. One thing. 2, who says that it's not useful for engineering? We have a lot of papers in the literature for use of game theory in engineering. At least I have seen one of them. Someone had used game theory for water engineering. And it was cited a lot. I don't know if you know Kaveh Madani. He has a paper. Kaveh Madani works in UN right now for water management of the whole world. And for doing checking what we should do with the water crisis in the world, they had analyzed it using game theory. So I'm saying that it's useful for engineering a lot. Also, in terms of pure mathematics, in that way also it's useful to analyze different games that we see in the world. Also, it's good for finance. Some part of the some of the students in this class are from management science, and game theory is good for them as right. You can say I'm right, yeah. Then in finance, it's very important because we have especially duopoly and these things. We'll see that. We'll see that. So some slides of this slide deck are inspired by teachings of Professor Stanko Dimitrov here at U Waterloo, and this book is also important by Eric Rasmussen, Games and Information and Introduction to Game Theory. Let's have a break, and we come back at 17 to 9. We will cover mixed strategy and continuous strategy. We will see an example in management science. Okay.
Honest question, slightly off.
Okay, just before we go to the next slide, let me tell you that Bayesian Nash equilibrium was proposed by Harsan Yi in 1967. As you see, it's old. By the way, in game theory, you also have Harsan Yi transformation. Let me tell you what it means. You never ask me what if the nature does not move first? What if it moves in the middle of the game? In this case, there is something named Harsan-Yi transformation to bring nature to the start of the game, and that game will be equivalent to the previous game before moving the nature. Okay, so there are some transformations called Harsan-Yi transformation to bring nature to the start of the game. Okay, that's one. So let's go to the mixed strategies. So far, the action space was discrete and finite. Do you agree? It was the action space. Each player had 2, 3, 4 actions, right? Something like that. But what if the actions are continuous, such as price, volume, etc.? What if the action is setting the price? The price, you have a lot of a continuous range for the price, right? These things. So the strategies for discrete actions are pure strategies. They call it pure strategies. But because the players choose one of the actions each. So a strategy I is a map from Wi, I think it was the realization of the game, which is response by the strategy, and then the action AI. So a map from the realization to the action AI is the strategy. That's the purest strategy, right? But what is the strategies for continuous actions are called mixed strategies, because we may have a mixture of actions and not pure actions, hence the name mixed, a mixture of actions, right? So as you see, rather than AI, I have M of AI. What is M of AI is the probability distribution. So do you remember the probability density function? So this is a probability density function for the ith player to play action AI. Of course, this M is greater than or equal to 0 because probability is non-negative, and its integral over the action space is 1, right? Because it's the PDF, probability density function. So a completely mixed strategy means that the PDF is always greater than 0. It never gets 0. So sometimes if M is greater than or equal to 0, it means that some of the actions in this continuous range might have probability 0 and we never do them, right? But when M is greater than 0 strictly, it means that all of the actions are possible, even with a small probability. Okay, that's completely mixed strategy. Consider the welfare game. You remember the government and the pauper? You remember they had and it does not have a pure Nash equilibrium. Do you remember? I think we talked about it in the previous session. There is no pure Nash. So if you want to see 2, 3, it goes like this. 3, so minus 1, 0, it goes like this. Here, 0, 1, it goes like this. Here, 3, it goes like this. It never ends, right? So there is no pure Nash equilibrium. Also, there is no pure dominant strategy equilibrium if you calculate. So why? Because here, so we have 2, 1. Here we have 3. So 3 is better than 2, but 0 is not better than 1. So I can't eliminate any column. What about rows? So let me think. Rows. 3 is better than -1, but -1 is not better than 0. So we cannot eliminate any rows too. So it doesn't have any pure equilibria, either Nash or the dominant strategy. However, it has a mixed Nash equilibrium. Okay, it has a mixed Nash equilibrium. Let's see. So we can consider probabilities for playing the actions, such as theta for probability of action 8, as you see here. And 1 minus theta should be the probability of action no 8. Of course, the probability of actions per player should sum to 1, right? So probability of action look for job for pauper, let it be gamma. As a result, probability of action not look for a job will be 1 minus gamma. You see that? Okay. Now, that was an example of what I mean. So basically, what does this mean? With probability theta, government will 8. 1 minus theta, it will not 8. With probability gamma, the pauper will look for a job. But with probability 1 minus gamma, it will not look for a job. So it became probabilistic, right? The actions, playing actions became probabilistic. As a result, a strategy became probabilistic. Right? Nash equilibrium in mixed strategy. So in the mixed strategy, we can find the Nash equilibrium with 2 approaches. So how do we find equilibrium in the mixed strategy forms, right? Now I'm talking about it. 2 ways at least to do that. First order condition or payoff equating methods. We'll talk about both of them. Okay. First, let's talk about first order condition. So what is the expectation or expected value for discrete random variable x? Do you remember? This is a definition of expectation of a discrete random variable x. And I think don't get worried. It's very simple. It says that multiply every state of that random variable by its probability and then sum them up over all cases, all states, right? This is for discrete. If it is continuous random variable, this summation becomes integral. Okay, and P of x is the probability for taking the value x, right? Then let's calculate the expected payoff. By the way, expectation is usually used when we have some randomness, right? So the expected payoff for government player is what? Theta. So according to this, the probability times its value, right? So theta, probability theta. Then for this theta, we have, which first off, we are talking about the payoff of the government. So only these are important, right? But which of these are important? Only these 2. Why? Because I'm talking about theta right now. So theta times 3 times gamma. As you see, what is the probability that this 3 happens? Theta times gamma, right? This is exactly what I did. But here, also, what is the probability that -1 happens? Theta times 1 minus gamma. But as these 2 terms both have theta, I'm factoring out theta. So theta times 3 gamma plus -1 times 1 minus gamma. Okay. Now I go to the other row, 1 minus theta. What is the probability that -1 happens? We are talking about payoff of government. 1 minus theta times gamma. What is the probability that 0 happens? 1 minus theta times 1 minus gamma. Right? And I'm factoring out this. So if you calculate these, simplify the terms, it becomes 5 theta gamma. 5. It becomes 5 theta gamma minus theta minus gamma. Some terms cancel each other. Okay? Becomes this. Now let's calculate the expected payoff for the pauper player. Then what happens? Of course, as it is pauper, we should consider only these payoffs. So 2 its probability is, now let's consider this column and this column. So the first column is this, the second column is this. The first column, gamma times theta for 2, gamma theta. Probability that 1 happens, gamma times 1 minus theta. Gamma 1 minus 1 happens. I'm calculating the expected value, right? So probability that 3 happens, 1 minus gamma theta, and the value is 3. I'm putting in equation 4 the expectation. 1 minus gamma theta and 3. What about 0? Its probability is 1 minus gamma times 1 minus theta. So you calculate them, simplify the terms, it becomes this. This is the expected. So what is this? Expected payoff for the government. What is this? Expected payoff for the pauper. As you see, we can calculate the expected payoffs for the players. Okay. Now, for the first order condition, what does it do? Forget this. Flashback to high school. You have a function. You want to find its maximum. What do? Take derivative. Set it to 0. That's called first order optimality condition in optimization. Okay. So whenever you have an unconstrained optimization, such as maximization of a function, the first thing which you should do, take derivative, set it to 0. If you can find a closed form solution, done. If not, you need to do it iteratively, right? Such as first order or second order optimization. And by the way, we can check whether it's a maximum or minimum or saddle point by checking the second order derivative, the sign of second order derivative, right? If it is multivariate, rather than sign, we don't have sign. Then the second order derivative becomes a Hessian. We should check whether it's positive semi-definite or negative semi-definite, right? Okay. Do you understand what I'm talking about? No? This is maximum. This is minimum. This is saddle point. Maximum, minimum, saddle point. In all of these 3 points, the first order derivative is 0. So when you take derivative and set it to 0, you might find any of these. But how do I know this is maximum? I can consider the second order derivative. Here, by the way, second order, it's the sign of second order derivative shows where the function is facing. If the sign is negative, it's facing down. When the second order derivative is positive, it's facing up. When sometimes negative, sometimes positive in that area, it's saddle point, because here it's facing down, here it's facing up. Right? So you can find out, you can separate between these conditions, which one it is. Okay, now we have expected values. I have expected payoff. Should I maximize it or minimize it? Maximize it, because payoff is good, right? So I have the payoff of the expected payoff of the government. What is my parameter? What is my, I should take derivative with respect to what? Theta. Why? Because theta is the probability for government, right? Government doesn't have any access to the probability gamma. Probability gamma is for the pauper. So I have this, take derivative with respect to theta. becomes 5 gamma minus 1. Set it to 0. Gamma is 0.2. Right? And you can also check the second order derivative is 0, which is less than or equal to 0. So it's facing down. Okay. Because note that this is also facing down and its second order derivative is 0. Okay. The expected value of Popper was this. We calculated that. Its optimization variable is gamma this time, right? Because Popper, its probability of actions is gamma and 1 minus gamma. So take derivative with respect to gamma and set it to 0. Theta becomes half. Okay. So far clear? The second order derivative is 0, which is less than or equal to 0. Good. So we can check. And I said, please check it. Hopefully it's not a minimum, right? Because if it is a minimum, it's worse. You're minimizing the payoff. You want to maximize. Now, we found the best probabilities for the equilibrium, right? In these probabilities, the expected payoffs of both government and Popper maximize, peak, right? So in the equilibrium, government, so what do these mean? In the equilibrium, government will aid with probability half and will not aid with probability half. The Popper will look for a job with probability 0.2 and will not look for a job with probability 0.8. No. Theta is 0.5, so theta is the probability for government. Gamma is the probability for Popper, and gamma is the probability for looking for a job. Okay. By the way, if you modify these payoffs in this table, these probabilities will change definitely because the expected values will change. For these payoffs in the equilibrium with higher probability, the Popper becomes lazy. This and will not look for a job. If you change the payoffs, for example, if the government fines very harshly, then probably the Popper becomes active, right? Do you see what I'm talking about? Okay, this now, as you see, we found equilibrium in a mixed strategy. It's probabilistic, right? So take a look at this. Now, the other case, the other way to calculate the equilibrium. So the first one was first order optimality condition, right? The other one is payoff equating method. What do we mean? In the payoff equating method, when a player uses a mixed strategy in equilibrium, it must get the same payoff from each of the pure strategies used in the mixed strategy. So otherwise, if not equal, then the rational player plays the strategy with higher payoff more frequently, that is with probability 1. I mean, what do I mean? Consider the payoff of government for aid. Also the payoff of the government for no aid. Of course, they are probabilistic. They should be equal to each other. Because if one of them, in the equilibrium, I mean, they should be equal to each other. Because if one of them is slightly greater than the other one, that player will definitely do that. It becomes deterministic, not stochastic anymore. Because the player is rational. And a rational player always wants to maximize its payoff. Do you see the idea behind payoff equating method? Because it is assuming that the player is rational. Therefore, these two at the equilibrium, these two should be equal to each other in the expected value, I mean. These are expected payoffs, right? So let's see. Payoff of the government for aid. Let's see, how do we calculate this? It's a bit different, by the way. That was payoff of the government in total, right? Now this one is the payoff of the government for aid. Let's calculate it. So what does it mean? For aid, I mean, I'm in this row, right? And the payoff becomes what? 3 times gamma. the probability that 3 happens is gamma, not theta and gamma anymore. Theta times gamma. Because I'm definitely talking about this row. Okay? So now the probability is still, this is expected value, but its probability becomes gamma, not theta times gamma. Also, -1, its probability is 1 minus gamma, not 1 minus gamma times theta, because we are definitely in this row. Likewise, probability expected payoff of no 8. See this row? No 8. -1 times gamma, 0 times 1 minus gamma. Likewise, let's calculate the payoffs. Where are we? Here. Now, talk about look for a job. 2, of course, payoff for popper. 2, its probability is theta. 1, its probability is 1 minus theta. What about this one for not look for a job? 3, its probability is 1, its probability is theta. 0, its probability is 1 minus theta. Right? So far clear? Now, these two should be equal to each other in the equilibrium, and these two should be equal to each other. Let's see. So as you see, payoff equating method, set these two to each other, equal to each other, you will, and solve it for gamma. So set these two to each other and solve it for theta. In this payoff equating method, you set the expected values of governments equal to each other, you find the probability for popper. See the difference? In first order optimality condition, you take derivative with respect to its own probability, you find it. But in this one, you set them equal to each other, the probability of the other one is found. Okay? As you see, interestingly, the results of these two methods became the same as expected. Okay. So in the equilibrium, government again will aid with probability half, and the popper will look for a job with probability 0.2. Okay. Now we also have categories of games. So I talked about how to find equilibria in Nash equilibria in mixed strategies. Done. Okay. Now categories of games with mixed strategies. So we have several categories which are important in the literature, I'm telling you. One of them is discoordination games. So consider these payoffs. AW, these are values, right? Some values. And in the discoordination games, we have such a, do you remember when we wanted to calculate the Nash equilibrium? We used arrows. If you draw the arrows by comparing the values of, for example, here A and B, you will see that B is greater than A, so you draw arrow in this way, okay? The arrow in the discoordination game will be either completely clockwise or counterclockwise, okay? We call these discoordination games. And as a result, either A is greater than C, D is greater than B, X is greater than W, and Y is greater than Z, or the other way around. C is greater than A, B is greater than D, W is greater than X, and Z is greater than Y. One of them is clockwise, and the other one is counterclockwise, right? Agreed? Okay. Interestingly, these games, they don't have any Nash equilibrium, right? Pure Nash equilibrium. But they have a single equilibrium in mixed strategies. They have a single the Nash equilibrium in mixed strategies. Interesting. Example is the welfare game. We just calculated its Nash equilibrium in the mixed strategies in the previous slides, and we saw that it had a single equilibrium. Another type of game in mixed strategies is coordination game. So the previous one was discoordination game. This is coordination game. And it's like this. The arrows become like this. So basically, it has two symmetric equilibria in pure strategies. So it has two pure Nash equilibria. This and this, right? Agreed? and one symmetric equilibrium in mixed strategies. If you calculate that, it will be like this. By the way, for arrows to be like this, A should be greater than C, D should be greater than B, W greater than X, and Z greater than Y. For arrows to have this. By the way, how to calculate these arrows? Look at the previous session. In the previous session, we talked about how to draw these arrows in the for finding Nash equilibrium. Okay. So example is ranked coordination game. So compare these values. So for example, A in this game is 2. X is -1. B is -1. W is 2. C is -1. Y is -1. D is 1. Z is 1, right? And as you see, these inequalities hold for this game. And if you write these, for example, if I'm here, 2 is better than -1. So this is the arrow. If I'm here, 1 is better than -1, 1 is better than -1. So I'm drawing here. If I'm here, 2 is better than 1, draw -1, 2, -1 is better. And here, 1 is better than -1. So exactly the arrows will be like this, right? This is coordination game. It has 2 symmetric equilibrium in pure strategies and 1 symmetric equilibrium in mixed strategies. Very interesting. So when a game has pure Nash equilibria, it might have also mixed Nash equilibria too. Worthy to find, right? So another category is contribution games. Contribution. So like this, we have, so the arrows will be like this, but this time, as you see, pure equilibria are these 2 cells, the other diagonal, right? And for this to have, we should have C greater than A, B greater than D, X greater than W, and Y greater than Z. Moreover, we have either B greater than C and Y greater than X, or C greater than B and X greater than Y. Okay? So it has 2 asymmetric, by asymmetric I mean the other diagonal, asymmetric equilibria in pure strategies. By the way, you know why we call it asymmetric, right? For example, these are same actions, action 1, action 2, action 1, action 2. In symmetric equilibria, either they both do A1 or both do A2. In asymmetric equilibrium, one of them does A1, the other one does A2. They do different actions, right? Do you understand what I'm saying? Okay. So, and also 1 symmetric equilibrium in mixed strategies, right? So we talked about these important categories, and again, inspired by teachings of Professor Stanko Dimitrov at the University of Waterloo, and this is the book, Games and Information, an Introduction to Game Theory, and this is the reference, right? Any question? No? And the other one is, let's see how much we can cover it, and we will continue it in the next session afterwards. So, continuous strategies and duopoly. Continuous strategies. Continuous strategies refer to when the action space is continuous. It's a bit different from mixed strategy. In mixed strategy, the actions are discrete, but we have probability for performing the actions. In continuous strategies, the action space itself is continuous, right? Okay. It is slightly different from mixed strategy, as I said. So, duopoly. Because duopoly, we are going to analyze some duopolies using continuous strategies. Duopoly, again, this is good for finance people. Duopoly means 2 companies are competing in the market, and they are usually dominant, okay? Such as Google and Meta. Monopoly means that one company dominates the market, such as Google in the area of search. Although Bing is trying, but I think Google still is dominant yet. Okay. Monopoly and duopoly. 3 Most well-known models of duopoly are Cournot competition, Stackelberg competition, and Bertrand competition. Have you heard of this in management science? Yeah. Okay. So these are famous between management people. Okay. These three. So these games have continuous strategies. These games have continuous strategies where the actions are continuous. How do you pronounce it? Cournot, or I don't know. Cournot competition. Okay, Cournot competition. So you can see how old they are. Cournot competition proposed in 1838. Okay. It has continuous strategy space. It is a duopoly in which two firms choose output levels or quantities in competition with each other. So what do I mean by output levels or quantities? How many, for example, assume they are chocolate companies. How many chocolates do they produce? Okay. And also they have simultaneous moves. This is called Cournot competition. Every company makes QI quantities. Okay. So the first one is Q1. Q1 chocolates makes Q1 chocolates. The second one makes Q2 chocolates, Q2 quantities. Okay. Actions are choosing quantities, Q1 and Q2 simultaneously. So they are doing it simultaneously. So for example, the first chocolate company says, I make 100 chocolates. The other one suddenly at the same time says, I make 150, right? So the marginal cost per making quantity, we have some marginal cost usually when we make something, right? Because you need to use some materials to make some stuff. So let it be C, denoted by C for cost. And for example, 12 here, right? We also have demand in finance or total generated quantity, right? Because whatever they generate, it is the demand of the market, right? They want to buy it. So Q, capital Q, is a summation of Q1 and Q2, right? The profit per quantity is this. So they also have profit, and the profit is assume 120, although you can change this number, but 120 minus Q1 minus Q2, right? So Q1 is let me think, because they are making these Q1 and Q2. I don't know why they have. Do you have any idea why they use this function? Because it's a famous function in finance. You know why they use 120 minus Q1 and minus Q2? I need to think about it, but they use this as a profit. Just give me a second. I think it makes sense. Why? When you increase the quantity, the profit, I think, should reduce. I think that's the case. Yes. For example, yes, I think we saw it. At least my analysis in my mind. When PlayStation, the latest PlayStation came, the number of PlayStations in the market was, they just made very few number of PlayStations. They became very expensive. The latest PlayStation. They made maybe 5,000, something like that. Too few number of PlayStations. Each of them became very expensive. That's the reason. When you increase the quantity, the profit goes down because it becomes cheaper, I guess. Okay. The payoffs of the players then is this. Player 1, player 2, the payoffs. So the profit times the quantity, its own quantity, Q1, right? Because this is profit per quantity. So times the quantity minus cost times the quantity, right? Because per quantity, or also per generating quantity, I also have the cost C. I need to use my stuff, some initial materials, right? So now simplify this term, it becomes this. Likewise, the payoff of the player 2 is this profit times Q2 is quantity minus C times Q2. Again, with the same analysis. It becomes this. So these were the payoffs that we talked about. Then the first order conditions, let's use the first order conditions, similar to the mixed strategies. Yes.
Payoff formula,
Yes.
would it be profit minus cost if profit is revenue minus not?
So profit minus cost times the quantity. All right. So factor out, for example, here, factor out Q1, it becomes P of Q, the profit minus C times Q1. Right? So whatever you have the profit minus your cost times the quantity. Right? Yes. Yes, I think this is by the way, a value. You can change it. You can change it. So let me analyze this more for you guys. First off, minus Q1, minus Q2, both. Why? First off, you understand the minus, the reason of minus. I just told you. When you generate fewer number, especially when you are famous, when you generate fewer number of things, it becomes more expensive. I think another example is Samsung or Android versus Apple. Apple makes fewer number of phones, I believe. We have a lot of Samsung phones across the world, right? That's the reason Samsung is cheaper. Okay, but Apple is more expensive because they generate less, or Apple laptops, whatever. We have a lot of other laptops, but Apple laptops are fewer. So that's the reason for minus. Another reason, why do we have minus Q1 and minus Q2? Because in duopoly, if one of them makes a lot of things, the whole, we'll have a lot of them anyways in the market. Any of them which generates more, the total number of products in the market gets larger, so the profit goes down. So because it becomes cheaper. I'm saying that even if one of them is making a fewer number of products, but the other one makes a lot of products, still the profit goes down in the market because the price goes down. And that's 120 is a constant. Maybe we have some intercept, okay, for this profits, because you can have some plus some constant, right? Any other question? I think we don't have enough time. So we will conclude the session here, and we'll at the start of the next session, I will go over this again. And we'll see the different competitions in the market. Okay, thank you. Thank you.